Thank you all, everyone. So they don't make podiums for tall people today. So I'm going to be doing this a fair amount. Hopefully that's OK. So yeah, my name is Matthew Rockland. I work for Anaconda. Anaconda does a variety of things. We sell software. We also make the Anaconda distribution, which are using the NumPy pandas space. You might download Python that way. And we also write open source software. So I work in a library called Dask, which is for parallel computing. I usually speak at data science-oriented conferences or science conferences or computational-focused conferences. This one's a little more broad. I'm curious, how many people have heard of and have a decent understanding of what Dask is? OK, so that's like a third to a half. For you third, there's some stickers over there. I've got some more in my backpack if you want. This is not going to be a super high-level overview of Dask. I give a lot of talks about Dask, and there are some good high-level overviews. I actually recommend the PyCon 2017 talk. It talks about Dask in general and how it fits into the rest of the Python ecosystem. In this talk in particular, I wanted to reach out to the non-data science folks to try to answer this question. So I prioritize some of the work that happens on Dask, and I want to know if we should start prioritizing more Celery or Airflow-like computational tasks. And that's the thing that I'm trying to answer, and I'm hoping that I can inform some of you all about how Dask works. Then after the talk, you can inform me about what's important in that space. So that is my objective in this talk. So to give you more context of that objective, let's look at parallel programming in Python generally. So again, Dask is a library for parallel programming in Python. So you run many things at the same time, either using your many cores on your laptop or using many machines on a cluster. Dask can be used for that purposes. Generally speaking, it tends to be used in this central data science space. So Dask is commonly known for parallelizing libraries like pandas or NumPy or subsets of scikit-learn. But if you're in Python, you might use other systems, right? You might use a single machine situation. You might use the multiprocessing module. How many people have used the multiprocessing module? Okay. How many people have used concurrent futures? Okay. Ideally, those do the same hands. If you're using multiprocessing, please switch to concurrent futures. All of the core Python people would like you for that. You might also use cluster technologies. So there's older systems like IPython Parallel. There's new fanciness, things like PySpark. And Dask is usually lumped into this space. However, there's also other systems like Airflow, Celery, and Luigi. Show of hands, who uses these systems in this crowd? Yeah, so the conferences I usually go to, it's almost nobody. So I'm in the right place. Yeah. So these systems are used often for maybe more complex workflows or more custom ad hoc workflows that aren't necessarily a big table you want to do MapReduce computations on, but I want to run this thing every hour. If that fails, I want to run these two tasks on top of that. Something like that. And I'm again, interested in this bottom space. So usually, again, Dask talks focus on machine learning and NumPy and pandas and that computational space. So I'm going to give a very brief example. Dask array is a library built on top of Dask that parallelizes NumPy. So it's many NumPy arrays, maybe spread around a cluster or many threads on my computer. And what Dask array does is when you write down some NumPy-like computation, so you're computing the singular value composition, matrix multiply, some transpose, Dask array translates that into hundreds of little Python functions that have to run against each other to compute the whole logical effect. Similarly, Dask data frame composes many pandas data frames, again, across a cluster, et cetera. These libraries transform these high-level operations into a task graph. Looks like this, where there's many Python functions that depend on each other. This is actually a task graph generated from a scikit-learn cross-validated grid search with a pipeline. So these graphs can be quite complex. This is the kind of picture you might see in the Airflow docs or the Celery docs. And then it's Dask's job to execute this graph efficiently. So at its core, this is what Dask does. You give it a graph, it executes that graph efficiently, given whatever parallel resources you have. So I'm going to give a couple of very quick examples about that. So I might have So you can run Dask in a single thread. You can run Dask on a local machine. I'm going to use the distributed version on a local cluster just because it's simpler. Ooh, I don't want to run that yet. One second. I also have a supercomputer waiting, and things got a little confused for a moment. So we're going to do things locally first, and then on a larger cluster. Yeah, that looks better. Ignore the errors. I'm on master branch. Yeah, so I might make an array. Whoops. Let's bump up that up. Whoa. I might make an array. It's a random array of, so it's a 20,000 by 20,000 array cut into chunks of size 1,000 by 1,000. And what you saw here on the right is you saw Dask identify that what we were doing and said, okay, great, I need to make a couple hundred small NumPy arrays using the random function. And so we saw that run. Let's, now I do something simple like, let's say, compute the sum of x, maybe along some axis. And Dask will again go ahead and compute that for us. And computes that by running thousands of little Python functions. So on the left, they're sort of like the data scientists are happy. They can run NumPy or pandas, but on parallel data. On the right, we are running many, many small Python functions across distributed hardware. And that is again, sort of like this picture. Right? So we're running lots of small Python functions. Now, Dask scales. So just to show that, I'm going to connect to a cluster over here. So here I'm doing the same thing, but now we're connected to a terabyte cluster sitting actually in Colorado. And I can do the exact same thing, right? Dask.array as da, x equals da.random.random. Maybe at a 10,000 by 10,000 array, cut into chunks. So all the NumPy arrays will be smaller. They're going to be 1,000 by 1,000. We're going to ask Dask to go ahead and put that into memory for us. So that runs, quite a bit faster. Because we're a bit bigger, we can bump that up by maybe 100 times. Again, we just allocated 80 gigabytes across a cluster that's sizable, and we could do fun things. Let's take y, let's define that to x plus x transpose. Let's also subtract off the mean across some axis. If you don't know, math and algebra, that's fine. You don't need to know what this means. But again, you should appreciate that Dask is computing all those things for us. All the red here is communication. So taking a matrix, flipping it around, adding it to itself, that's forcing all the computers to talk to each other. So we're seeing lots of red. All that's communication. And Dask has, little nice things. It has things like distributed profilers. So we're actually asking all of the threads, what they're working on over time, and we have a little time series of that. So Dask does parallel execution well. I'm going to claim that it actually is one of the most sophisticated task schedulers that exists, especially that's accessible to Python. So that's me showing you that Dask does things well. Dask, however, does some things not so well, and that's again my question. So other projects like Airflow, Celery, Luigi also compute task graphs. They tend to be worse at computational aspects like latency or data transfer or throughput, but better at things like policies around emailing you or retries or complex interaction policies. And so the question that I have is, should we make the effort to push Dask into that space, providing more computational abilities, but again, at the effort cost, we now need to build a lot of features like retry logic. And that's again the question that I have in my head that is undecided, but I appreciate feedback from you all on. So again, Dask runs efficiently is what it brings to the table. So it can operate with arbitrary data dependencies. It's not like Spark or MapReduce, which have sort of stages of maps and then group bys and filters. It's completely arbitrary task scheduling. It handles Python in a very nice way. It handles resource constraints like GPUs. It's also very efficient. But, hundreds of microseconds of overhead, 10 millisecond round trip times. If you have this inside of a web application, users are not going to notice that you're using Dask. It's very, very fast. It operates usually much, much faster than users can experience. And it scales to thousands of nodes. But it lacks things like Airflow has. So as an example, let's look at the Airflow tutorial. So here's, go to Airflow, look for tutorial is what you'll find. And this is what Airflow gives you, right? There's nice things here, like I want to run this at a particular time, going every hour. I want to email me if a task fails. Dask was not built to email you. It is built to crunch numbers as fast as possible. That being said, Airflow is maybe a little bit more verbose. You have to sort of define every kind of operation you want to do ahead of time. There's some costs here. So Airflow was built and designed around a certain set of problems that Dask was not built around. So should we try to sort of bring things over? So Dask has some failings. And those of you who raise your hands about Celery and Airflow, I'd love to chat with you and see if, do you care about latency? Is that something that you really like? Or do you not really care that much? Do you really care about getting emails? Okay. For us to talk, some more examples of Dask working outside of the traditional NumPy or Pandas space. Again, if you really care about scalable data frames, you should go onto YouTube and find some other Dask talk. There's fun talks dealing with large data frames across clusters. It's all very exciting. Okay, so my favorite library in the standard library is concurrent futures. If you want to get some parallelism in your code, you should use concurrent futures. You shouldn't use Dask. So concurrent futures is a lot like the multiprocessing module or the multiprocessing thread pool, but it's a little bit cleaner and it integrates with some other tools. So if you have a function like this function here and you call it, Python will block. It will wait until that function finishes. Concurrent futures lets you call that function in a separate thread, and it immediately returns to you a future that you can then block on some future time. But between you blocking on that future and you calling that function, you can do other things, right? So this is parallelism. We can do two things at the same time. You can also launch many futures, and they'll all run at the same time based on how many threads you have. Dask supports an interface. So if you like concurrent futures, you can use Dask as drop-in replacement, but it'll now run on a cluster if you so desire. This is useful in a few different situations. The first situation is parallel code that is not a simple map or not a simple data frame computation or an array. So when we built Dask, we sort of took it to lots of academic collaborators, lots of industry people, and they said, hey, great, we've got parallel problems, but they don't look like big data frames. They look a little bit weirder. So here's some code that very clearly has parallelism in it. We're looping over a couple of loops. We're calling either F or G based on some condition. And they said, hey, great, we've got code that looks like this. Can you parallelize this? And so how do you parallelize this? It's not quite about something different. So concurrent futures lets you call all those functions with futures separately. Then you can block on all of them at the end. So it was a very, very lightweight interface that let us sort of tackle a lot of other problems. So for Dask, it looks the same, but this uses the same task scheduler we saw before. The thing that was powering the array computations or the data frame computations, it's also powering these computations. This is what we end up finding was very useful. We talked again, machine learning researchers, they like this a lot. People building complex pipelines, they like this a lot. Another sort of interesting case, which comes up in a few cases. So I've got here a web server running Tornado, and my web server gives you back the Fibonacci number that you give it. And so inside my little function here, when some user clicks on my web page, we call the fib function, which is defined up here. And then we write that out to that page. Okay. Now, if you've taken any computer science programming class ever, this function is very, very slow. This is the canonical example of a very, very, very slow function. And so you might want to shove that off, not to do it in your own local thread, because that'll block your server while it's running, but you might ask concurrent futures to run that on some other process. And here we can do it very easily. Tornado is very async aware. It's aware of concurrent futures. They can play nicely together. With Dask, we can do that too, and we're also a little bit more new, so you can use fancy async await syntax if you care. But it's really, it's the same thing. So let's go and look at that, actually. I think I have that sitting over here. I think I do need to disconnect my supercomputer. So that program is running. And it's running with Dask. So whenever I hit this page, we're firing off that computation with Dask, and we get a result back. So every time I hit refresh, you'll see that Dask is running that task on some thread, on some other process. Now, if we sort of zoom in here, fib of 10 is actually, even though our implementation is very, very slow, fib of 10 is actually pretty fast, right? So this is running at, a few hundreds of microseconds. So let's see, if I try this really hard, sometimes I can get it to use 2 threads at once. No. Let's bump it up a little bit. Let's see if we can engage any parallelism at all. Yeah, that's a bit fatter. Maybe that'll work. Nope. Let's bump it up a little bit more. Whoops, that's definitely too long. Yeah, so here we see that as we have sort of larger computations, we're using more of our threads, right? And this bottom thread here is busy computing, Fibonacci of 230. It's probably going to be a while on that one. But what's sort of nice here is that we're getting nice response times back. When this was fast, we got back from Dask in around 10 milliseconds, right? It was a very fast response time. We also scale out to a cluster. We also scale out to however much we want. So this is Dask being used in not at all a machine learning or data processing context, but a web backend context, which is sort of maybe different from what you normally expect from sort of big data frameworks. Okay, I'm going to pause here for questions. I have more material, but this is a good breaking point. So, any questions? Yeah, so the question is, more broadly, if I have a bunch of tasks that are being fired off, can I then submit more tasks on top of those tasks to build up more complex chains? Absolutely, yes, Dask can do anything you like. I'm also guessing you're in financial services. No, okay, your question was very financial services-y. Sure, sound processing, signals processing. Yeah, and Dask has been used in those sorts of cases before. Yeah. Yeah, so can you access the results of individual tasks atomically? Yes. The answer to most of your questions will be yes, Dask can do that thing. Yeah.
Is there some concept of task priority? As computing Fibonacci is more important right now than prime factor or something?
Yeah, so this is a great example of a feature. So yeah, the question is, can I assign priorities to tasks and say these kind of tasks are more important from these kinds of resources maybe, I care about this sort of task queue. This is something where systems like Celery or sort of the queuing systems are very, very sophisticated. They can say, these kinds of tasks are on these kinds of machines, they have these kinds of priorities. Dask does have a prioritization system, which it uses internally, because it identifies that this task is really important because all these other tasks depend on it. We don't really expose that to users very often. Our data frame users don't care most of the time. But yeah, that's exactly a great point of something that we should be working on if we choose to go in this direction. We have all the technology, we just haven't exposed that out to users. I'm not sure I entirely understand the question, but I'll state an answer, and maybe that will be the right answer. So the question, I think, is, I'm running some code that's parallel in my cluster, I'm running some code that's locally, sometimes I have to coordinate between those two. How does it make sense? How do you coordinate those things? Yeah, so in Dask, you can run things locally, run things in your cluster, you can scatter data back and forth, you can wait on data that's computing remotely, and then based on some partial results, you can compute more work. It's a very general task scheduling framework. I'm not sure if that does things. Okay, let me switch back to content. I think I have about 5 minutes. So there'll actually also be a lead into CJ's talk, which is next. So I've also been thinking a little bit about streaming systems recently. And so one common use case for task queues, systems like Celery, is if I have to build pipelines that respond to signals as they come in from the real world. So maybe every day a new file gets dropped into some default directory. Maybe I have a real-time, financial time series data source coming at me. And so none of this is at all real code that will exist in the near future. There's just something we've been sort of playing with. So we've been playing with APIs that we can build on top of Dask that are maybe a little bit easier to build out these sort of more complex systems. So this is a tiny library called streams. And if you make a function, let's say, so the goal of streams is to build pipelines that handle continuous data. So data sets that don't have any termination point. So here's a very, very simple stream. And when I push data through that, that element has the increment function called on it, and then has the print function called on it. What's nice, though, is that I can do a couple of these. So the same. Okay. And I can start building up pipelines in this way. So streams is handling moving data through pipelines. This gets more exciting if you start adding things like data frame computations onto it. So here's a source of streaming data frame data. So source dot, let's just print. So here's a continuous stream of pandas data frames. And I want to do something instead, like let's take x.sum, oops. So can we, instead of moving individual functions through, start building more complex pipelines that do maybe some more interesting complex things? This is all running just in a local thread with Tornado. This handles things like back pressure, branching, joining. If you sort of care about pipeline systems, you'll care about those things. It's all running just locally in a single Python thread. It's not parallelized or sophisticated at all, but it can all run on Dask. So Dask can also serve as an engine to this system. If you care about these sorts of things, again, you should come talk to me. This is, again, super experimental. So please don't use this in any production system, but please do come talk to me if you have thoughts about how this would be useful. So that's it. Thank you all for your time.